The purpose of this lecture is to describe the algorithm to compute cohomology groups from homology groups. And in this lecture, I have just collected the properties of home and ext from the book of Dummett and Foote on abstract algebra. So let us start with the properties of home. So the first property is home of this integers z comma g, where g is any group. So this is any group. So this is equal to g. Home of zn comma integers is 0. za zb is equal to zn, where n is nothing but the greatest common divisor of a and b. Home of zn comma g, this is nothing but isomorphic to kernel of g to g times n. And then you have home of a direct sum with b comma g, this is equal to home of a comma g plus, or you say direct sum here, of home of b comma g. So you can immediately see that home of 0 comma g is 0. So we are going to use this later on. And all these properties you can find in Dummett and Foote. Now here this zn is nothing but z modulo nz. So this is what is the z subscript n. Now we talk about properties of ext. So ext of zn comma g is gn modulo ng, and in particular you have this result. So this is an important result, we are going to use this later. Ext of zn comma z is zn. Ext of a comma g is 0 if a is free. For example, ext of integers comma g is 0. And in fact we are going to use this result again and again, that ext of this integers comma integers is 0. So ext of a comma b is 0 if nb is equal to b for any n in natural numbers. Ext of a comma g is 0 for g equals to q, r and c. So any of these three fields of rationals. So this is rationals, reals and complex. Then again you have direct sum a plus b comma z. This splits like this, and you can immediately see now that ext of 0 comma integers is 0. Again this result we will use. Then 6 is if you have this zm plus f. The zm basically means that you have this m copies of integers. So these are m copies, and f is a finite abelian group. So if you do like this, you just get f. Now 6 is nothing but it is a consequence of this 2 and 5. So first you write it as 5 and then you use 2, and that's how you get zm comma z is 0, and you just get f comma z as f. So these are very important results, and all of them we are going to use to compute cohomology groups. Now our formula was this. So the cohomology group of a space, so space is S. We are going to find, we are taking the group G as integers. So we have integers here. So this we mentioned in the previous lectures, that this is iso to ext of h I minus 1. So this is the homology group. Direct sum with home of h I comma z. This is again the homology group. So this is homology group, this is homology group, and you have the cohomology group right here. So this will now make sense. We will do 3 examples. The first example we do is of a circle, and you know the homology group of the circle is the 0 and the 1 group is integers, and the rest of the groups are 0. So for I greater than 1, all these homology groups are 0. So now we start plugging in, put I equals to 0 here. So you have x of h minus 1 comma z. So h minus 1, you take this as 0. So you have x of 0 comma z. So x of 0 comma z is 0. So this term is 0. And you have home of z comma z. So home of z comma z is just integers. So again, you can write like this. Property 1 we are going to rewrite as home of. So as an example here, so this is what we are using here. So h0 is integers, so you have z comma z, so this is just z. So 0 direct sum with integers, you get integers. Now put I equals to 1 here. So you get h0 comma z home of h1 comma z. So the first focus here. So this h1 is integers, we get it from here. So you have z comma z, so this will be just integers. Again, we are using this property 1 right here. What about this? So this is h0 is again integers, this is integers, so x of z comma z, and we know x of z comma z is 0 right here. So this is 0. So this will again give you integers. h2 x of h1 comma z, again this h1 is, so you have x of z comma z, again x of z comma z is 0. So this thing is 0. Home of h2 comma z, so h2 is 0, so this is 0. Home of 0 comma z, so home of 0 comma g, or you can say here for example home of 0 comma integers is 0. So you have 0 here again, so you have 0. So you can check this cohomology groups of the circle will be 0 now for I greater or equal to 2, or you can say I greater than 1. So you can see that in this case of circles, the homology groups and the cohomology groups coincide. So second example we will talk about is torus. So again, the homology groups of the torus, 0 is integers, h1 is this direct sum of integers. So again, I'm going to use this formula right here. Instead of I, we are going to plug in I equals to 0. So h minus 1 we will take as 0. So again, x of 0 comma z, so this entire thing will be 0. And you have home of z comma z. So this h0 we will plug in z. So home of z comma z, home of z comma z is z. So you get z here, you get direct sum of 0 with, so yeah, this integer is nothing but this is the same as this one, just like in these two cases here. Now you plug in I equals to 1 again right here in this formula. So x of h0 comma integers, so h0 is again integers, so you have x of z comma z, again x of z comma z is 0. We're using this result right here, and this will become home of, so we are going to use this as result right here. So this will become home of z comma z direct sum with home of z comma z. So home of z comma z is integers, that this again is integers, so you get z plus z. Now we talk about the cohomology group H2. Again you have x of h1 comma z, so this will be z plus z. So this will become x of z, and this you can rewrite as, this we will rewrite as x of z comma z direct sum with x of z comma z. Now we are using this property number 5 right here, but this is 0 and this is 0, yeah, from here, from this property. So this entire thing becomes 0. Home of h2 comma z, we know the second homology group is integers, so home of h2 comma z is home of z comma z, which is just integers. So you can now compute that higher cohomology groups are all 0. Homology groups and the cohomology groups, they coincide. Now we do the Klein Bottle. So again, for the Klein Bottle, we have computed the homology groups. You have integers here, and you have z direct sum with z2 for h1. Again, you have hi is 0 for I greater or equal to 2. Again, you use the same formula right here. You plug in I equals to 0 here. You get this formula. H minus 1, this is x of 0 comma z. So this will be 0. You have homomorphism of z comma z. So this is just integers. So h0 is clear. Now we talk about h1. Again, plug I equals to 1. So x of z comma z, this is 0. Again, we are using this result. And now you see h1 comes here. So you have home of z plus z2 comma z. Use property 5. This becomes home of z comma z, direct sum with home of z2 comma z. So this is integers. This z2 comma z, so now you use property 2, n is 2. This is 0, so you just get integers, and that's what we have here. And now you come to the cohomology group H2. So x of h1 comma z, again h1 is z plus z2. So now we are going to use property 6. So here, using property 6, you have m is 1 and f is z2. So m is 1, f is z2. So this becomes just z2 by property 6. And you have home of h2 comma z. So h2 is 0. So this will be home of 0 comma z. So this is 0. So you just get z2. Now notice in this case that the cohomology groups are not the same as homology groups. So in the cohomology group, you have a cohomology group in H2, and there is nothing here in H2 here. In fact, this Z2 has shifted up. So this is shifted to H2. So the torsion part has shifted up. So this is an important point. And so by using just these rules here for home and next, you can compute the cohomology groups of all the spaces for which we have already computed homology groups. So if you're given homology groups, you can compute cohomology groups just by using this formula. And these properties of home and ext. So we have already computed 3 examples here.